So today's discussion is titled as Structured and Time Series and Language Models. So the presenters are Rrubaa and myself, and we have moderators like Sylvian. So this is the agenda we suggest for today's discussion. First, we're going to define or to compare these different models, structured versus time series versus language model. And then we will spend more time focusing on language model, and especially the traditional approaches of a language model. The new approaches like RNN, right? Those are going to be discussed in the future sessions. So we will leave discussions on RNN to the future sessions. We will just focus
not RNN, just the basic neural architecture.
Yeah. And then particularly we find this word embedding, the embedding technique, whether it's embedding words or embedding the categorical variables, are particularly interesting, and we would like to discuss further on this aspect. So first, let's compare this three different type of models. Structured models, examples of structured models like house price prediction, because each data point is a structured object, postal code, which somehow indicates the location of this house, whether there's a transportation hub, whether there's a good school nearby to this house. So I think that will influence in the selling price quite a bit. And then we also have seen image classifiers. The inputs are images, which is basically non-structured data. If we flatten all the RGB channels, basically it's just a bunch of numbers. And time series, we think that stock price, predict tomorrow's stock price is a typical example of a time series model. In this model, we know all the informations until now, and we try to predict what's going to happen tomorrow. And then, and the language model is mainly a sequential model. In the sequential model, the training points, data points are sequence of words. From the sequence of words, often the task is to predict what's the most likely next word, given the sequence. Or sometimes it can be backwards, like you look at the sequence of words and you look at the words, somewhere in the later part of sentence and try to predict whether the first word is a name or is a place or is something. So, but nevertheless, all this is the words have a temporal, kind of a relationship, right? The words in front and the words and the nearby words, whether the words in front or whether the words behind it, there's some sort of relationship. These are the typical sequential models. You want to add anything?
Yes.
So, so first thing is what exactly differentiate from the time series versus the sequential model. Our understanding is that for the time series, we only know the current, and then we try to predict the next. we never know the next come back to predict. That make no sense, because if you know the stock price tomorrow, then you won't be bothered to predict today's stock price. But in the language model, we just given a sequence of words, which the words here and the words in front or the words behind, they are sort of related. So we think that's the main difference. Don't know whether everybody agree or anybody has a...
So what's the difference between the time series and the model? Actually, they're both time series models.
The language model has a clear grammar underlying. So for a language model, you have additional rules which you basically can learn. So you know that there has to be a verb in a normal sense. In a time series, you have no such additional grammar information.
Okay. So that's partially correct. A language model also doesn't usually have a concept of a grammar. It usually has the concept of what we call Markovian assumption, which is that the nth word depends on n-1 preceding information. So it uses contextual knowledge just as a time series, type of time series model. Usually when we talk about time series, we mean a regression of some value, right? The stock market price. For language models, we usually don't mean that. We usually mean pick one out of n things, and could be a very large number, right? So if you think of a language, you think of the number of vocabulary items, it could be very large. Right? In our information retrieval class, we teach, that the language model can output any one of the dictionary words of English or another language. So it depends on the size of the dictionary. So usually that's around 40,000 different lemmas or word forms that are in the dictionary, not the inflected ones like plurals, tense. So that's what you find in English. On the web, of course, there are lots of spelling variations. There are lots of changes in how people use language. So the amount of vocabulary is much larger, maybe 500,000 per million. And so when you go to Google Corpora like that, where they calculate how many word forms there are, just practically limitless. So actually the set of possible tokens that you can have in a vocabulary is limitless, effectively limitless when you go to a very large size, because there are empirical laws that have been observed that say when you grow the language bigger, you get less new tokens coming in, but there will always be more tokens. Okay, so you can think of the language model as predicting an infinitely large set of tokens, but for the restricted practical sense, you would say maybe around a large size, maybe around 40, 50,000. You're right to say that underlying the process of creating language, we usually think of it as having a grammar. Okay, but the language model doesn't have that sense. It just has empirical data backing up its observations, right? So if I've seen, please turn off your, then you can guess what the next word is for it. Mobile phone, or right? Something. So those are all prediction tasks. They're categorical prediction tasks, but they're conditioned on context. They're like a lot like a supervised classification is what we done in this module earlier, right? When you're saying try to differentiate dogs from cats or dog breeds from another dog breed, but the vocabulary is a lot larger. It's basically on a okay. Just as similar to other time series prediction tasks, though, we usually don't condition it on the full historical time series, right? So we won't say we need to predict the stock price of tomorrow's, I don't know, SGX stock price based on all the days that SGX has been active, right? We'll just say condition it and say, okay, I only need the last 2 days worth of data, and that's the Markovian assumption. I just use yesterday's data and the day before's data to predict today's data. And we would call that a language model of size 3 or a time series model of size 3, because you have 2 pieces of contextual data to predict today's. Okay, sorry, go ahead.
But I have a question. So if we are going to predict the stock price, the training data points will be, we take all the historical data. So, we take every 2 days stock price, and then we find out the next day after this 2 days. That's one training data, and then we have a large sequence of such a set of data using that to do our current prediction.
Right.
So that sounds like it's a bit quite similar to the language model, isn't it, in a sense?
Yeah, it is very similar. I would say the major difference between the language model and the time series general type of time series is usually when we talk about time series, we're usually regressing, right? Meaning predicting the NUS value.
Okay.
Right. In language models, we're predicting a specific output, categorical output in the word, right? Or some data associated with the word, its inflection, whether it's tense, whether it's numbered, or whether it's gendered, right?
In case of stock prices, you always have this micro trends and macro trends. How the market is working, there is a seasonal impact or something like that. If you just take our day context, we are just missing some macro variables. How to take around those macros? Because like after 10 years, there will be a recession. There is a probability of having a recession after 10 years.
Right, that's a good point. In time series, there's usually global context or local contextual data that you would need to factor in. In language models, you don't see so much of that. Typically, in language models, you're predicting, let's say, words within one sentence, and each sentence is an independent problem from the next. Okay, there's not that much work right now to model entire texts, right? Although you can use the same type of RNN features as you're limiting down. Okay. Things tend to go bad when you try to predict very, very long sequences. Okay. So yeah, definitely when you go to predicting larger trends, you need to have maybe different granularities of predictions, right? Let's say you're seasonal or year-long time series data would influence the predictions at the more fine-grained level. Do you want to say more about that, Rrubaa? Go ahead. Anyone else?
Language models it can be shifting what you have there. You have used for some certain grammar or words. So with current it shifts gradually. So even that is taken into account for the language.
It can be, usually not. Yeah, because usually when you're employing a language model, you're using it for some specific purpose. Think about the autocorrect on your phone, which is a language model. Certainly, we don't really worry about the archaic forms of it, right? Because we're more concerned about people in Tokyo, Shibuya, making up new words and new usages of words all the time. So those neologisms, coining of new words are more important. Yeah. You can do language model prediction, and scientists have on long-term effects, what they call diachronic linguistics, like when you change time frames from medieval times to current times, what has changed, how usages change. You can track that through Google's model, right? So Google has, as you probably know, digitized quite a lot of books from a very long period of time, and they can track language usage of certain things. Yeah. Other points you guys want to raise? Go ahead. Oh.
Yeah, I just wanted to say that, like, even in the shorter term, that language probably has a similar, like, large or mid-scale context as the stock market. Like, it's a different, like, a situation you're in if you're like talking with friends or like writing a formal piece of paper. So not just a sentence, but also knowing, okay, this is a scientific paper, helps you predicting. I'm not sure that's covered in any model.
Yeah, so that's exactly right. So many times we talk about this in the context of language. I don't know whether you're over it, but it really depends on the training data you train on, right? If you get a language model, all the training data from Shakespeare, it's going to predict words like Shakespeare. Right? On the other hand, if you give it the NUS SMS corpus, which was assembled in my group, it'll start sounding like 16-year-olds looking for places to eat. Okay, that's what it does. That's because the vocabulary and nuances and languages, the words that come after each other. So it very much depends on the language you train on. So definitely when we're building autocorrect for your phone, you're not going to train it with a language model that you got from web pages. That would just be wrong. Right? You won't predict probably. Right? You'll see. You can try this. You can go to the Google Ngram by just typing Google Ngram in your phone or your laptop, and they have systems there that can tell you a little bit about it. There's also a very large corpus of words from the Stanford web call. It has a couple billion tokens, and you can get words frequency from there, which can tell you a lot. What's the 20th most frequent word on the internet? You'll never guess. It's the word copyright. Why is that? Every footer has the word copyright. It's not a normal word in English, but you'd be surprised that if you look at a language model that's constructed over web pages, that word is going to come up quite often. Okay, so that's why the corpora matters a lot. Right? If you train on a corpora medieval English, you'll have medieval effects, and likewise, that's a very good point. So actually, people are always worried about language models when they make autocorrect. That's why you have to have frequent updates, because the world, as we know, changes very fast, right? I don't know. Last year, Donald Trump probably wasn't so much. Well, maybe that's not a good example. He's been in lexicon for a while, right? But you can come up with new words, neologisms all the time. They get used, they get thrown away. They're quite faddish, and a language model needs to update that, especially if you're doing auto predict or auto correct, because people use those neologisms all the time, right? And they also get outdated. Like Tamagotchi used to be a hot thing. It's no longer in most people's vocabulary, right? Maybe some of you don't even know what it is. I don't know. Example one would be Rocket Man, right? Or what's the phrase that Kim used to call Donald Trump?
Dotard something, is it?
Some phrase that's not very common in formal.
Okay, so let's continue. So finally, we want to just compare a sequential model, a language model versus non-sequential model. Suppose you are officer registered the newborn baby's names, right? And so you can see that names as a sequence of words, but obviously you cannot predict the next baby's name based on the previous baby's name, because there's no relationship at all. It's not like the normal language, right? So the language really depends on the previous, keywords.
Yeah, so baby names exactly exemplify this type of problem of seasonality and long-term effects. You go to baby name, if you're a parent to be or you're a parent, maybe you have consultants for baby name lexicons. But there are some on the net, and now they like the seasonality.
Okay, thank you, Kuan. So let's look into a bit more about the language models. So as we already explained, the language model is the task of assigning a probability to a sequence of words, or task of assigning a probability for the likelihood of a given word to follow a sequence of words. These two are actually equivalent problems, and you can derive one from the other. So if I put into the mathematical notation, you would be able to realize that probability of predicting the nth word given previous n minus 1 words is the joint probability of n words over joint probability of n minus 1 words. So the left hand of the equation is the probability for the likelihood of a given word to follow a sequence of words, whereas the numerator in the right hand side is probability for a sequence of words. So these two are actually equivalent problems. So this task actually requires a human level intelligence. Why is that? So let's say you're going to predict the next word for the sentence, Adam was born in France and his native language is what? So if your model is only looking into the second sentence, it may even say it is English, maybe because it's widely used and it's even grammatically correct, but conceptually wrong. So thus requires the knowledge of previously appeared words and also the synthetic and semantic information of the language that you're working on. And what if there are so many sentences appearing in between those two sentences? Then the problem is going to be a bit more complicated. So hope you got the idea how critical the task is. So language models plays an important role in natural language processing and AI. It's a crucial component in real-world applications such as machine translation and speech recognition, where the system predicts different translation or different hypotheses, and language model is used to score them. For example, in speech recognition, the language model is combined with an acoustic model, which models the pronunciation of words. So acoustic model is going to predict different candidate sentences with their corresponding probabilities. And language model is used to reorder them based on how likely they are to be in a sentence. So all these models works based on the assumption called Markov assumption, as we already discussed earlier. So the idea behind the Markov assumption is, if the sentence length is really, really large, it's not feasible for us to consider the entire sentence. So we are going to simply make an assumption saying the future is independent of past given the present. More formally, the kth order Markov assumption is the next word of a given sequence only depends on previous k words. So we are narrowing down our problem where we try to predict the n+1 word given previous n words where n is really, really large, to predict the n+1 word giving the previous k words. K can be even small, like 2, 3, or 5, even maybe large. So there are several traditional approaches based on Markov assumption. I will quickly go through them so we can realize the major drawback in traditional approaches. So the main idea would be to take the count of occurrences in your training corpus. So in order to predict the n+1 word, we are going to count the occurrences of sequence of k words with the n+1 word you are going to predict, and the previous occurrences of the k words alone. So that's going to directly give you the probability for the predicting word. So there are different drawbacks with the baseline approaches. Even if you just see the equation, let's say what if the k sequence are not available in your training corpus, then your observation is going to be 0. Then the denominator becomes 0. So there are different techniques like smoothing techniques to overcome that. And there are different approaches implemented on top of baseline to overcome the issues and to improve the accuracy. For example, one is a skipping model. The idea behind skipping model is, if you haven't observed the entire sequence of words in your training corpus, you just back off and skip some of the words and give a good probability to the skip sentence. For example, let's say you haven't observed show John a good time in your training corpus, but you have observed show Stan a good time. Then if you are going to predict the probability for the sequence show John a good time, the baseline approach will give you the probability 0 because you didn't observe that in your training corpus. So idea is to skip the word John and give a good probability that is almost close to the probability for show Stan a good time. And there are other approaches like clustering, where you just cluster the words and use that to predict the next word. For example, let's say you have observed party on Monday and party on Wednesday in your training corpus, but you have not observed party on Tuesday in your training corpus. But you have clustered Monday to Sunday together. So it's going to increase the likelihood of the word Tuesday to follow the sentence party on. And there are so many other approaches. So what are the limitations in these traditional approaches and why we move to the neural architecture?
We should stop for a second at the last slide. Does everyone follow all these problems or solutions for dealing with training data and how to overcome their limitations? Question? Okay.
So what are the limitations of traditional approaches and why we move to the neural architecture? Any idea?
Because of the first thing, the data is just so much big data, so you have so many entries, and it's not able to really model all those things.
Okay.
And with that skipping factor, when you skip something, you have to measure the distance, what is the distance. And it's not feasible to really measure so much distance with so many computation power. And with the increase in data size, obviously your traditional models are going to saturate at a point. You need a neural network that can work at a very good stage even with then your traditional models is dependent upon your own working or sense of the topic. Like if you're very good in that, you can generate with the feature engineering, you can generate a good model, but everyone will not be able to do it. So that requires a great amount of human skill. So I think with neural network you can certainly compromise certainly on the human skill, and then you can just put it on a very big data to get the required results in a very efficient.
Do you agree with that?
Okay, so that's correct. So the word that you used to say that you can compromise the human level knowledge in the neural network, that's actually the generalization of the context. So that we are going to discuss. So one major problem is scaling. So if you are going to consider k grams, that means k number of sequence to predict the next word, then it's going to give v to the power k number of combinations for your observation, where v is your vocabulary size. It's a million number of words. So you may argue that not all the k-grams are valid, and not all the k-grams are going to occur in your training corpus. But still, it's going to increase your number of observation multiplicatively. And the main limitation is lack of generalization. So if I put into an example that you will be able to realize that more. So let's say you have observed the word teams to follow the words 3 and 4 in your training corpus, and you have observed the word groups to follow the word 4 in your training corpus. But that does not going to influence the probability for the word groups to follow the word 3. So that's a major problem in the traditional approaches. And we are going to solve, yeah.
Wouldn't clustering have exactly against
No,
that?
clustering is other way around. So clustering is you're going to predict the next word based on clusters. So that's what my example is. So party on, you have clustered Monday to Sunday together. So you have to replace Monday with Tuesday. Here the example is different. So teams follows 4 and 3. So that means 4 and 3 are somehow related. But that does not knowledge is that knowledge is not going to help you to predict that group is going to follow 3. Those two are different problems.
But isn't there like trivial extension of the problem?
Yeah,
cluster
teams and
approach?
groups can be clustered together, but we can come up with different examples where you can't cluster.
Yeah, but like he said, won't it be trivial to look at the order?
I mean, I'm not on it. So the clustering approach always has a problem that in some contexts you can cluster things and in other contexts you can't.
Okay.
So but I mean, to have like two clusters and to say one element of one cluster is behind the other, that raises the probability of all cluster combinations. Isn't that what you would do if you would follow cluster approach?
So in the clustering approach that I explained, in that one, you're going to use the cluster to predict the next word. You're not going to utilize the relationship between previous word to predict the next word. That's the problem there.
I think is it that if we see that 3 and 4 they are in one cluster, and team and group is in another cluster. So what he says is that if our model learns that this cluster followed by this cluster, so likely you will have 3 and group.
Yeah, in this example, it will work because the word teams and groups may be clustered together, but we may be able to come up with examples where we can't cluster them, but they are context in the context it's almost related.
Yeah, but I think this slides, or what we want to say is that indeed we want to find the semantics of this words 3 and 4. There are in certain semantic they are very closely related. Group and team in certain viewpoint they are very closely related. So actually the next topic of embedding is really the thing which help us to solve this problem. But if you just look at a naive and very simple way of modeling, you just view all your words are distinctive words in large vocabulary. Let's say the vocabulary is 30,000 different words. Then you lose all the semantics. You cannot do clustering, and then this is the problem. Right?
Yes.
Yeah.
So you're going to cover one part and embedding?
Yes, yes. That's our next topic. Yeah, exactly. Yeah.
But then it's about the size of the clusters and the size of the vocabulary. One problem with the language modeling approach is we're treating all the vocabulary as one part, which means exactly what Jiang was saying, is that you have possibly 30 or 40,000 entries. And when you go to a 10-gram model where you have more than one token as context, that memory requirement, right? To store n-grams of size 1 requires 30,000 entries. To store n-grams of size 2, all 5 grams, then you require 30,000 squared, right? And 30,000 cubed per trigram. So even Google, I had a student who went to internship at Google. They did at most 6-gram models, which is a lot, right? 40,000 to the power 6 number of entries. So that means to predict something, you're going to find contextual words and then you try to predict. So it doesn't scale very well when you consider vocabulary analysis of state, right? But exactly what you're saying is that if we cluster things together, we can shrink the dimensionality of this vocabulary, right? And so this is what we're trying to do. Right, is to extend the notion of clustering, but do it in some more agnostic framework rather than just doing it semantics, just look at distributional properties, and that's where we get embedding. That's a really good point. You want to say anything more?
No, I don't. I know embedding, so I'm just saying embedding.
So I think clustering is an approach that many people have tried before. If you look at the embedding literature, it builds on previous work. So there's other things that you may have learned prior to embeddings, which is like, for example, LSI, which is unturned based on top of singular value decomposition. So if you know linear algebra and you've taken enough of that, you should know singular value decomposition, which is the basis for the original approaches for things like embeddings. It's basically building a low rank approximation of a very large matrix. We can go over that if you'd like more.
Okay, so as a solution to the problems that we discussed, we are going to move to the neural architecture. So can anyone tell what is word embedding?
Who wants to take a shot? I think everyone's sort of heard of it.
Yeah.
Right, so maybe you can go around the room and just put together a couple words or phrases from each person and then see how correct the collective wisdom is. Do you know about word embedding?
It's like, as I say, some words put together but categorized as per the meaning or opposite, how closely related they are.
There are many contexts. There are many contexts in which you can see it. Like you have the words and you have the opposite words. So you have a subset and then you have a set and you have subsets. So you can have a synonym and anonym, and this is how basically the dictionary or the language grammar is there. So you try to take the things from there and try to embed it on a space, how they closely related they are.
Yeah. So you take the words, maps them into some dimensional space, and so you can capture that some words are close to other words in one dimension, and you try to find that in an empirical fashion rather than like before saying, okay, I know that Monday, Tuesday is related. You just let machine learning do its magic. Okay.
Yeah, and one type of doing that is like the one-hot encoding method, where you can, where you map it into like a huge dimension, in which every like the word, every unique element in that vector is a one corresponding to unique words. Way of doing it.
A real definition
kind of relationship and find self worth and then use the same relationship. Yeah, I agree with the vector she said.
So as far as I know, it's just you start with one hot encoding, and then you try to compress it down to a certain number of dimensions, so that because you have to learn how to represent those concepts with the lower dimensions, it can sort of cluster the reasoning, the meaning behind each of the words together, I guess.
For me, I guess it depends on how you train your word embeddings, but the general idea is that you want to place them in some latent space of some high dimensionality latent space such that the locations of each word have some meaning.
I guess the three of you are presenting.
So similar to a picture might be a representation of a person, word embedding is a representation of word in real valued numbers. So it's arranged in a way such that it represents the synthetic and semantic information of the word and also the context of the word in the way that computer can understand. So by encoding the word into some set of digits like 100 or 200, you're going to get more information about the word. As I told, the synthetic and semantic information of the word and also the context of the word. So if you can see the image, so this is the projection of word vectors in a very low dimension. So it's actually projected in a very high dimension like 200 or 300. So you can apply some dimensional reduction techniques to bring it up to lower dimension. So you can see it's manifests some interesting characteristics. For example, if you just subtract the man vector from the king vector and add the woman vector, the resulting vector will be almost close to the vector queen. And surprisingly, the difference between the vector walking and walked will be almost equal to the difference between swimming and swam. So you can realize that it's the word embedding has not only learned the semantic information of the word, but also the synthetic and grammar up to some degree. So it's really, really interesting, and Kuan is going to talk a bit more about the word embedding.
Okay, when I see this slides, I think the slides is, I personally like it and also dislike it because I like it because, yes, okay, it very clearly describe, word embedding basically is to put words into dimensional, translate the word into a vector, okay? This vector is in a certain dimension and maybe usually it's a 100 dimension. Right, so this dimension, 100 dimension, is much smaller compared to the original vocabulary dimension. You have a vocabulary of 30,000. That's a very high dimension. Now we try to map into a low dimension, although 100 dimension is still quite sizable, but compared to the original, it's much lower. And the purpose is that when we have this vector represents the words. Each of these dimension can relate to certain semantic, right? So one dimension could be representing gender, or one dimension could be representing whether this is verb or versus noun, or whether this is past, tense of this verb. So sort of things. But then I dislike it is that because the dimension itself is not human manually pick, this is the dimension we decide, this 100 dimension we decide, this 100 dimension, and we map every word into this fixed 100 dimension. The dimension 100 dimension is learned by the machine. The machine will figure out that, it finds out, maybe use this 100 dimension, it can help to reduce the loss function. So it sort of like automatically learn that one. The slides didn't really call up that aspect of the dimension is not manually set. It is learned by the machine.
Yeah. Okay. I think I also don't like a lot of these visualizations because they're very they're very appealing, and they get people very excited about the semantic power of words. They're quite powerful, but they have a lot of drawbacks as well. So it's the sugar coating on something that people don't quite really understand that well. I think the important thing also about embeddings is it's general. It's not something that's specific to. You can use the idea of embeddings wherever there's context-sensitive information that you wish to encode. So we use it for words because words are defined by the context they occur in. Very famous linguistic quotation by Furth, which says that you know the meaning of the word by the context in which it is. Right. So many times when we hear new words, we can figure out what they mean based on the pragmatics, like how you say it. Like if you're frowning, if you're angry, of course that's not usually a good word. All times to introduce a new word, you probably want to use a curse word. The other words in the meanings in the words context can help convey. So those are all important parts of embeddings, right? So people have used in all sorts of contexts, and regardless of whether you're going to use it in language models, if you're an NLP researcher or a security researcher or an OS researcher, there could be cases in which you can use embeddings.
I just wanted to mention that, actually, after you two explained, I see these graphs a little bit different than before. For example, like king, queen, and man and women. There's not really like a dimension that means gender because the arrows are not like lined up to the dimensions. It's just like some distance.
Yeah.
Also on the white side, like okay, so capitals and country is somehow related, but it's not like it learned a strict relationship. It's kind of go a little to the right and maybe a little down. Like it's messy to a certain degree.
Right. So you can explain this in vector operations, right?
Yeah.
Basically, what they're saying is the difference between some of the capitals and the countries. That vector, the average vector, activates words similar in the neighborhood of the other ones, right? So if you take the vector represented by Russia, you apply the vector that represents the difference between a country and the capital, you get fairly close to the word for Moscow.
If you, for example, would use the vector from Spain to Madrid and would apply it to Vietnam, you would end up with Beijing.
Right. Yeah. So these visualizations aren't great. They're collapsing a lot of dimensions, right? We have actually a fairly high dimensional space, 300, 500, and we're plotting it in 2 dimensions to get that realization. That's why I sometimes don't like these visualizations. They gloss over the technicalities, right? But they convey something very nice that you can just do vector operations and you get. But the important part is the underlying concept in which those vectors arise from.
I think it's quite ridiculous that just by word co-occurrence locally and both globally, you get the words like semantic meaning. Has there been work done to include other things? For example, like word to back, like maybe the back of words model, the order of the words don't matter. But I guess in most cases they do, right?
They do and they don't. This is the really funny thing about language. People who study formal linguistics have always been concerned about rules and syntax. And those people who study linguistics, not to demean them or anything, they're doing something useful and good. They're coming up with a theoretical model for language. But in the stuff between our heads, we don't have formal grammar. Actually, we can try to learn them, but we don't apply them actually. We apply experience and the neuron distance, right? All the training that we have when we hear language, and that's more akin to what a language model does. So there's a famous quote by somebody who passed away, but who's a famous computational linguist that says, "The more linguists I fire from my team, the higher my translation score goes up." Or something like that. So the important thing is actually not the rule base that we come up with, but the amount of data we observe. Okay? The more data we observe, the better our modeling gets. And that's generally true for a lot of systems right now, is that neural network approaches work very well because they can harness large amounts of data and they can abstract away from what's important. Okay, so yes, everyone knows that language order matters. Yes, we know that doing modeling of gender and plurality and tenses matter for language. Okay, but a lot of times when we gloss over the details and we provision the model with one magnitude more data, the neurons can effectively learn a lot of those patterns. So we tend to right now have this blessing in curves, is that neural models work really well to the point where trying to put more semantics into our model backfires because we can just provision more data and the system will learn to some extent. There are exceptions, right? So everyone knows RNNs are largely inferior to, let's say, GRUs and LSTMs, right? Because those do have slight better accounting for long-term effects. But even those are somewhat inferior methods to actual state models that account for certain. So that's the long and short answer of it right now. Is that right now we're at the point where we can still gather large data, and the large data, when we use it effectively with simple models, seems to work. And there's not a lot of compelling reasons to go to more complex models until you have something really that cannot be modeled very well. Okay, so some of those are very long-term dependencies. Like if you mention somebody at the beginning, like I said, Tom, blah 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 blah. Then I have to pick a pronoun. You know, a short-term memory model may not know the difference between he, she, and it, right? And so you need the contextual knowledge that I had said somebody who's of a male gender earlier, and that will help pick it correctly.
I was thinking more on the lines of like relaxing certain assumptions made in the model, like that word order don't matter. So maybe like given less amount of data, you can actually form better representation.
I think people are still working on that. It would be nice to have models that are somewhat conditional. Once there's enough data, rely on a model that's been trained with, let's say, sequential word information, right? When I get to vocabulary where I simply haven't observed enough encounters of that, I back off to the generic word model, which doesn't have sequential, right? And if I have even more data, instead of just having sequence, maybe also add in case frames or semantic and syntactic information as what both linguists and natural language processing people, which are more empirical, have said are useful.
Do you think such a time will come when people will say, okay, we don't need more data, we can work with less data, but the data should be good?
That happens all the time, actually. Every day we have that, okay? It's just that when you look at big data and the public data sets that are out there, they tend to be fairly large, okay? Within a specific company, right, or within a specific domain, you may not have a lot of data. And worse, a lot of that data is not curated, meaning not labeled. Then you have no choice but to go back to the time-honored approaches, time-honored meaning 5 decades or so, okay, of doing feature engineering, right, which is to basically say, I need to know something about the domain. I need to model it in my supervised model, and I'm going to employ that for the purpose of learning something useful.
Yeah, actually, one of the keynote speeches for Rrubaa this year was mostly about everybody's shouting for more data, but they should be shouting for good data.
Yeah.
Yes.
So there's actually some approach to
In
some
WA,
towards
there
that.
was one talk in which they said, okay, we need less data, but a representative data.
Yeah, I think both approaches are valid. It depends on the type of problem you're tackling, right? Yeah.
And another interesting talk I listened to was about so Google tried to come up with an API which you can give a sentence and it tells you how poisonous the sentence. So that's of course you can use that in a forum and like to ban people who use too poisonous language. And they came up with a problem that in a sentence like "I'm a proud gay person" would be labeled poisonous. Because gay is used so often in a poisonous context that the word gay alone makes a sentence poisonous, even if it's totally harmless or actually positive. And they had the same problem, like they had lots of data. Like people from Google working on things with forums, you can imagine how much data they had, but the data was biased. So sometimes, like that's another example where like just having more data doesn't help you if the data is actually not really representing what you wanted to represent.
Yeah, I think that's a key part of what a data scientist's role is. Researchers should understand. Data has its limitations, right? You always want to do data analysis of what your model is actually doing, even if it's working appropriately. So I see many junior researchers, they say, oh, well, I got better results, so my model must be working, right? And that's usually a false, right? You can get good performance and bad performance from bugs.
I have to
Yeah.
edit.
Okay, next question.
Sorry.
Go ahead.
Okay, so for the interest of time, we have about 10 minutes left, 5 minutes left. So going to quickly go over the steps, because the steps of word encoding or embedding, I think all of you are already familiar. We first translate give every word a unique integer, and then do a one-hot encoding. And then from the one-hot encoding, we use this embedding matrix to transform that high dimension into a lower dimension. Okay, so we can skip this. Okay, so more about the architecture of this neural language modeling. Actually, nowadays we always use RNN. So this is prior to RNN. So let's skip this. Okay. So as Prof just now mentioned that this embedding concept can be used not only on words, can also be applied to other categorical variables, such as in the house price prediction and the postal code, right? The postal code, without using embedding, every postal code is just a unique postal code. One postal code and the other postal code have the same distance compared with this postal code and another postal code. There's no semantic behind these postal codes. But then with the embedding, the postal code can be translated into a multidimensional vector. And the good thing is the machine learning can automatically pick up what is the relevant dimensions for this postal code, which can facilitate our prediction to reduce the loss. So we see that embedding is basically a technique to reduce the dimension and also put some semantics into every words or every categorical variable. And it's good that it is learned automatically. Of course, because it's learned, if you there's additional learning, the parameters become the parameters in your model now, not only your normal multi-layer perceptron, you have all those parameters, but now you have another set of parameters you need to learn. So it makes your learning a bit more challenging. But the good thing is that most of the time the embeddings are pretty stable within a certain domain. Language embedding, people have come up with popular word embeddings, and we can always reuse those embeddings in our natural language processing.
Yeah, so the embeddings, as we said earlier, are like language models specific to a program. And so oftentimes, just like we saw in the image classification, you might have, like, say, the BGG model or another module that's pre-trained. You can adapt the word embeddings or retrain them to localize them for specific.
Yeah. So finally, I think we just want to highlight using this, summarize with this one slide. I think this is one of the things which we really feel quite exciting. We view the embedding is basically a way to automatically extract semantics from the words. It's a kind of a feature engineering. If we compare this with the CNN convolution, the filters, the kernels in the CNN, what does the CNN do? The kernels in the CNN do? Basically, it's kind of a feature engineering. The earlier filters learn the basic feature, and it progressively went towards the deeper layers. They try to learn more class specific features of your image. So in a way that embedding is doing similar work, right? It tried to uncover these words. What is a semantic, right? So we find this actually related. The idea-wise, they are similar ideas. So that concludes with our discussion here.
Okay. So embeddings, I think the most important thing to get out of embeddings is, there is something about specific to word embeddings, but basically, as long as you have some data that relies on contextual representation, okay, context can come from anything like postal codes, right? You don't generally think of them as contextual, but if you have, let's say, mention of something that's in a certain postal code and another, I don't know, another condo that's in a similar postal code, then it becomes contextual, right? So that type of hierarchical relationship gives context, right? In words, we'd say a sentence gives context because, as Jacqueline said earlier, the language models that embeddings are currently creating using Siebel or skip-band programs, they're not position sensitive, so it's just a hierarchical relationship, right? So as long as your problem has some contextual modeling, you can use the idea of embeddings to do that. And it's basically the same principle. Come up with a one-hot encoding, and then the one-hot encoding allows you to model the context because you can see other data items in that context and you model them. Then you fold them into a lower dimensional representation, right? And that lower dimensional representation, whether using SVD or TSNE or some other data reduction technique, you're going to get a smaller K-rank matrix, right, which you can assign to K. Usually that's tuned by a loss function or something like that. And then you use that to guide the rest of it, right? So yeah, both one-hot vectors as well as word dimensions are high dimensional. So you get that description a lot, but you have to realize the high dimensionality of embedding is far, far lower, magnitudes lower than what you get from one-hot, right? And that's the big problem with one-hot encoding is it's too sparse, right? When you try to squish things down into a low-rank approximation, things start to collide, and that's a good thing because you get some more semantics out of that part of what we want to do. But the embedding size is, of course, quite sensitive to the amount of data you have, right? The larger the amount of data you have and the more detailed your model is, then the larger the data size you have and the more simple your model is, the more data and the higher dimensionality. Right? When you have a more complex model, then you need to lower the dimensionality. So for example, if you put word order in there, or you want to put WordNet synsets, which is another way of that linguists have come up with, meanings. Okay? Or if you have less data, then you need to lower the dimensionality.
Practice, how do you use entity embeddings? I mean, because I'm just thinking like, for your input is always going to be one hot, right? So like, let's say the feature is day of the week, then be 7 vector with 6 zeros and 1 1. And then the neural network will already implicitly learn the meaning of these like one hot embeddings in like layers. So I mean, the idea of entity embeddings is that you just have another layer of weights that translates this one hot embedding into its like high dimensional like features. So there's no like point adding an extra layer there, because like if it's dense enough, like the network will learn it anyway. Because you're training these embeddings on the same task. So for example, like for the Rossmann sales thing, it's basically backpropagating all the way down to that new layer of weights. So and then you're using these same embeddings for the same task. So I feel like it's a bit relevant.
Well, for the entity embeddings for day of week, right? Because we were talking about that, they recommended having 7 days of the week plus one other, right? For placeholder for just a generic day. You can even introduce additional ones where you have weekday, something holiday, right? Then you're trying to introduce an artificial concept which might have meaning outside of the problem as well. So you could take that entity embedding and use it in another problem as well, right? But for that specific problem, I guess I'm not quite clear about what additional use it's doing in that problem. Do you guys remember? Because it was in
Yeah, the video, my understanding is that they mentioned that the day of week 7 days, right? And then the 8 plus, and then they embed into use half of it, right? So it's like 3 bits, right? So something like that. So my understanding is originally the Monday, Tuesday, they are of same distance because they're all perpendicular and they are all totally equal distance. But by doing some embedding, so somehow the machine learning is able to figure out maybe Monday, Tuesday, they are very close in certain contexts. So that makes this encoding more useful than the original one-hot encoding.
But the encodings were trained on the same task of sales prediction, right?
Yeah.
So that's what the dimensionalities of the days of the week capture.
Mm.
Then you use these same vectors to run through the same task of sales prediction, which. So I think in that case, the one hot and the normal one really has no difference.
I haven't watched that video. I think I've stopped one video before, but like what you mentioned a couple of times so far, like everything you do before helps a neural network and then becomes faster. So it's maybe you're right, like you could all do that in one step. But if you split it up a little bit and do some steps will always be true before, you save time later.
I think like we said that for the weekdays, for all the days we just have a embedding, so we can do it with 3 bits, 0, 0, and 0. We can have the distances. But we also can't have a one single column in which we have whether it's weekday day or a weekday. So when you have a weekday and weekend feature, then these 5 days are going to club in a very they are going to be close, and the weekdays farther than that. And that will actually affect our the whole model how it is settled.
So what I remember from that lecture is that he suggested taking all the date information and just writing it out as a large structure, right? So like day of week, whether it's a public holiday, whether it's a weekend or a weekday, etc. And then that large set of vectors would be squished into an embedding. Okay. So that can help because you're condensing that information to be more compact. So that the idea that Friday is the beginning of the weekend can come out in any point. But additional to what Jethro mentioned, which I think the main concern that you had is that you're doing the embeddings for the same task that you're trying to test on. What use is it, right? So my sense is that when you have an embedding form, let's say for day of week, you can pull in extra data from outside. So you can, let's say, go to the web, go find lots of corpora that happen to mention dates as entity. You can embed them into this space and enrich the embedding space, right? You don't have to just rely on the corpora from Rossman or another problem, right? And therefore, because you look at more data, but they're all still about days a week, somehow it's going to be more, right? So you can do that in a lot of cases, right? So even the word to vector, cloud vectors, they're mostly trained over newswire. So they're pretty good for news type of applications. For social media, they'll be almost useless because we don't spell tokens the same way in social media. you invent an embedding for social media, maybe you need to rerun word to back or glove or any other training procedure to create embeddings for that specific course. Any other things that you guys want to bring up? So I think embeddings are a really powerful architecture. They're basically an intermediate stop in the feature engineering. Previously, when we did feature engineering for dates and things, we'd have separate columns. But basically, the trick of embeddings is one more step. It says, don't stop there with your structured data model. Put that into a more compact representation to allow your data to intermingle with each other, right? This is the low rank approximation idea that comes out of SVD and LSI. It's previous techniques to doing embeddings before embeddings became popular, right? And so with that, you get a compact representation. It's a lot more scalable, as what Jiang, Kuan, and Rrubaa mentioned, because instead of having very high dimensional space, you have fairly high dimensional space. I don't know whether 300 is high or not, but that allows the portability of the model to be much better. Right? One of the big problems that Google had is like with 6 grams, it's terabytes of main memory data is needed to and even within word embeddings, if you store them into a neural network model, they're pretty big. They have several gigabytes in size, so it still has a fairly high, large footprint, especially if you're running an RN, or even much more if you're using a GRU or LSTM. Okay, I think you'll find that embeddings will reoccur in this course a couple of times, so we'll have a chance to go over the latter half of the slides more. So definitely your efforts there in preparation are not wasted. So we'll come. Okay.
Thank you.
All right. So we'll see you on Friday, this Friday. Those of you in week 6 should start to prepare. So if you are assigned week 6, do coordinate with your others in China. Okay. All right.
Prof, just to mention that you have scheduled the Good Friday to be the next Monday, right?
Yeah.
But that's a Sunday, right?
Yeah, I was told by Gabriella that it's the wrong date, so I'm going to move it back in.
Okay.
Okay. Thank you.
Thank you. Should we just leave the?
Yeah.
This is a laptop.
Yeah, I'll shut off.
Thank you. Prof.
Thank you.
Thank you.